Hello and welcome back to Calculus 3, section 12.9, part 2, problem 14. I think that's enough designation of what we're doing. So we're going to continue Lagrange multipliers, going to work on a number of examples, and then eventually switch to chapter 13. So for this example, where we left off last time, we are supposed to just find the extrema on the surface xy plus x plus y with the constraint of x squared y squared equals to 4. So just one more time, this equation over here will be called objective because this is what you are minimizing or maximizing, and this one over here will be the constraint. You better have two of these. Now, objective we label with f of x, y, z, whatever, and the other one is labeled with g of x, y, and so on. The formula which we are using to compute Lagrange multipliers is going to be the del f equals lambda del g. And we are remembering that the del is the vector of partial derivatives, and we just put the arrow above the triangle to denote that it's a vector quantity. So we are always going to have enough equations because the number of partial derivatives depends on the number of variables in the problem, and the lambda is additional variable, but we also have the constraint equation. So the number of equations, you will always have enough equations to find the variables. Now, as I said, you know, these problems tend to be annoying because we are getting those nonlinear systems to solve, and they can have you know, a lot of calculations or some tricks to compute and not too easy. But let's take a look at this. So first, I need a del f, and del f is the partial derivative in respect to x, in our case y plus 1, and then partial derivative in respect to y is x plus 1. So that will be our del f when we take the partial derivative of x and partial derivative of y of the f function. And now del g, we do the same thing. Partial derivative in respect to x is going to be 2xy squared, and the partial derivative in respect to y is going to be 2x squared y. When I equal these two with the lambda in there for the formula that we are using, so I have y plus 1 comma x plus 1 is equal to lambda 2xy squared comma 2x squared y. I get to equal the x, so sorry, the first component should be equal to the first component, and then the second component over here should be equaling to the second component times lambda as well, right? Because lambda distributes for both, and we get this. So let's take a look at these. So now I'm writing my three equations. First equation is y plus 1 is equal to lambda times 2xy squared. The next equation is x plus 1 equals lambda times 2x squared y. And the last equation is the g equation, which is x squared plus y squared equals 4. No, x squared times y squared equals 4. So these are our three equations. We have three unknowns, x, y, and lambda, and we do not care about lambda, ever. So when you are solving these problems, if you can eliminate lambda, go ahead and do it, because really there is no need to have lambda around. Generally, that's what I like to start. If I don't see symmetry in a problem that I can exploit, right, I generally try to kill off lambda and then deal with the rest of the system, right? In this case, solving one of the equations for lambda would be y plus 1 divided by 2xy squared, and then plug that. Now this is, again, this is me trying. Some of you might see a much better way to do the problem, much more efficient way to do the problem, and you should say immediately, there are no rules. There are no rules here. Just whatever works, go for it. That's technically what it is. So I'm going to use the first equation, solve for lambda, and so this is my general approach to these types of problems. I like to eliminate lambda because I just don't need it for anything. So instead of lambda in the second equation, I have my y plus 1 over 2xy squared, and that's times 2x squared y. Now, a lot of stuff cancels here, right? We have the 2 will cancel the 2, x will cancel the square, square will cancel the y, and this equation now becomes x plus 1 is equal to x times y plus 1 divided by y. If I multiply, right, y into the left side, I get xy plus y is equal to, when I distribute x on the right, I get xy plus x. And by simply subtracting xy on both sides, we have that y is equal to x. Yay. This is a big deal. When you get something like this, you're technically done. Because now I have that y is equal to x, and I also have that x squared, y squared is equal to 4, right? So what I can do is I can replace my y with x. So now plug in again and obtain x squared times x squared equals to 4, which is x to the 4th equals to 4. Taking square root of both sides will give me that x squared is equal to plus minus 2, right? But then I have to take another square root, and square root of negative 2 will not give me real answers, so I can just ignore that one, and we'll get exactly what you have, which is x equals plus minus root 2 by doing the square root again. So I'll put the square root on both sides with a plus and minus, and another square root of both sides with another plus and minus, omitting negative 2 as one of the answers. So I have that x is equal plus minus root 2, and then I am also, because, now I'll say because x equals y, right, we have that y is also plus minus root 2, right? So we have x is plus minus root 2 and y is plus minus root 2. This gives us the combination of 4 points, right? Which we'll have to test for their y values and figure out which one has the highest values and lowest values. But this gives us, right, so this system over here will give us root 2, root 2, root 2, negative root 2, negative root 2, root 2, and negative root 2, negative root 2. So we would have those 4 points. Now, to find out which one of these is the highest of all max values and lowest of all min values, you will plug this in one by one into the what do you call it, objective equation, and you will compute values to find z. Always remember that z was your f of xy. Your f of xy was given as something long time ago, xy plus, so I was xy plus x plus y. So now you will take f of root 2 to be root 2 times root 2 plus root 2 plus root 2, which gives you 2 plus 2 root 2, which you can leave that way, or you can go 2 times root 2 plus 1. But you're going to get the decimal. F of root 2 negative root 2 will give you root 2 negative root 2 plus root 2 minus root 2. These guys cancel, and you're getting negative 2. You will get the same if you calculate negative root 2, right? That gives you the same value of negative 2. And then finally you have your negative root 2, which gives you 2 minus 2 root 2, which is 2, 1 minus root 2. And this would be a negative number. This one is the max value because this is the only positive number that you have. This one has the highest elevation, the highest z value of all 4 points, right? And then over here, 1 minus the root 2, that's negative, call it, it's negative, about negative 4 point, sorry, negative 0.4, there we go, 4, 1. So multiply that in 2, so these two are actually lower than the one on the Now, as I mentioned, yes?
If you know that y is equal to x, can you still have like a negative and a positive for the x and y?
That's only in the solution of the system, right?
So that doesn't apply.
Doesn't apply for the point. Okay. Yeah. That's within the process. One of the equations that work out that way, but that is not the equation that we have that governs the system, right? The surface consists of all infinitely many points that create the surface of the surface of a printer, right? So again, for those of you that missed the last time, I had this image for you. I'm holding this the bottle, right? The squirt bottle, whatever it is, to clean the whiteboard. So what I did here, as you can see, is I drew this black line along the surface of this bottle. And I used this to contrast the two concepts, two calculations that we had. 12.8 min and max procedure, which would compute the min and a max of an object. If you observe, since I have this at an angle, there is the top point, the one when you put, if this ceiling is to collapse straight down, the first point that it touches on the top of this bottle would be the maximum value which 12.8 detects. If the ceiling is to rise up, the floor, if the floor is to rise up, the first point it touches on the bottom of the bottle would be the minimum which 12.8 detects. Now, what is 12.9? 12.9 are the points that are on the bottle, but at the same time they are on the black line which I drew. And the equation of the black line which I draw is your G. That's the constraint. We know that this bottle has the maximum point on the top and the minimum point on the bottom, and they're definitely not along this black line, right? So that's why the black line is called the constraint. I'm looking for new min and the new max subject to the constraint that I place upon you, right? And that has to be on the black line. So clearly, right, this point here would be the answer for the minimum, and this point here would be the answer for the maximum. Because it has to be on the bottle, and that is the So the shape and the surface of the bottle is the f of xy, and the g of xy is the black line. And then they work together. So Lagrange multipliers, right? Lagrange multiplier will give you this, and 12.8 will give you this. So that's the difference between the two. They're still looking for min and max. Now, in business, in engineering, right, you have constraints. It's not just min and a max. You have to compute min and a max in constraint to some constraint, right? With the constraints. So you want to maximize the profit, but, right? Maximize the profit constraint, let's not kill the population, right? Let's put that one, right? So your product has to be safe, your product has to be environmentally friendly, or whatever it is, right? And that will be the constraint. I mean, if those constraints did not exist, I mean, just imagine what Apple would do to the planet. Like we all know what happened in the Second World War. So it will be the same and worse, probably. So, yeah, constraints exist in business. All right, so let's go and take a look at another example of this.
So in this problem, there's two minimums?
Yeah. Which is, I mean, your car has 4. Motorcycle has 2. Cool, right? When you put it that way. Would you agree that your car has 4?
Yeah.
Beautiful. I hope so, right? Unless you have one of those weird European, in Italy, right? They have like one wheel in front. They also have that in Indonesia, I guess. Or, I don't know, whatever they're called. The first time I've seen him, it was in Italy. It was really funny. So let's take a look at one of these problems. If the book ever... Oh, come on. Let's take a look at more variables. For whatever reason, it takes forever to load. What we did 14?
Mm-hmm.
Okay. So let's take a look at something. So here is 95. It says f of x, y, z, again, as the objective function, is going to have x plus 2y minus z, and then subject to the constraint x squared plus y squared plus z squared equals to 1. By the way, what is this constraint? Sphere, very good. And what do I have as a, what is the dimension of this function here? What is the dimension of this function? 4. Very good. All right, so let's think about this a little bit, because this stuff exists. So here I have some kind of a surface, and this could be temperature. So I might be looking for the highest temperature or the lowest temperature, highest density, or whatever kind of characteristic you want to have within a three-dimensional object. You see, this printer here, this printer is 3D. It's in 3D, it's a 3D space, right? It has the length, the height, the width, right? But there are other things of this printer that also exist as its density and temperature and so on, and that could be added as the additional variable. So now I have temperature equals, and then you have this, which is the distribution of the temperature throughout this, and then I have a sphere, right, which I am observing inside, right, the core temperature. You have a laser in this thing, that thing gets really, really hot. It has the labels on it not to touch it because it's really hot. So that temperature is going to, right, go in a spherical, right, way in all directions. So what do I have? I have some kind of shape with some kind of thing that I'm measuring, and then I'm going to do it at the constraint within this type of a space, right? So that sphere is going to have the little top point, right, which should not be poking out of this printer, right, because I'm looking at the surface of the thing. You are designing something as an engineer that has to have extreme temperature inside to work. You don't want it to be scorching hot, right, on the surface if it doesn't have. Well, obviously stove, okay, fine, right? Stove has to have extremely hot surface for it to work, but the printer does not, right? You design a case in a proper way to shield from that unnecessary, right? Because you're not heating any external objects. Same thing with your car, right? The car is only 27% efficient. Where's the rest of it? Exactly, it's the heat and the noise and friction and all of that stuff that you don't need, right? So you have heat shields and things like that. All right, go ahead, have fun. This is your problem, you know what to do. 3 partial derivatives for f, 3 partial derivatives for g. Put them in a vector, set them equal to each other. Done. Let's take a look at this together. So we have our del f, partial derivative in respect to x, 1, partial derivative in respect to y, 2, partial derivative in respect to z, negative 1. Oh, nice. How about del g, 2x, 2y, 2z, nice. Now we're going to create the system of equations by equating all of these together. So I have 1 is equal to 2x, 2 is equal to 2y. Oh, sorry, this is supposed to have lambdas. Lambda x, lambda y. Negative 1 is equal to 2 lambda z. And finally, x squared plus y squared plus z squared is equal to 1. So here we have 4 equations and 4 unknown quantities. We can simplify some of this work. I can, from the first equation, say that lambda is equal to 1 over 2x. The second equation is that 1 is equal to lambda y, and negative 1 is equal to 2 lambda z. So now I can plug in this lambda into both of these equations, eliminating lambda. So I will have that 1 is equal to y over 2x, and I will also have that negative 1 is equal to instead of lambdas, 2z over 2x. And 2 is cancelled. So now, from the first equation, I have that y is equal to 2x, and from the second equation, I have that negative x is equal to z. So z equals negative x. Now I can feed these guys into the constraint equation and have x squared plus, instead of y squared, I get to write 2x squared plus, and instead of z, I get to put negative x squared equals to 1. So that's 6x altogether. 6x squared is equal to 1. Right? and x squared is equal to 1 over 6, and then we take square root of both sides, so x is equal to plus minus of square root of 1 over 6. Now you can rationalize this and get root 6 over 6. So x is plus root 6 over 6, and then we feed that into these equations to get x's and y's and z's. So y would be 2 times this, so has to be plus minus root 6 over 3, and z must be just negative of x, so it's also plus minus root 6 over 6. I mean, you can plus minus plus, but same thing. So there they are, and this is actually 8 points, right? This is 8 points. So the first point will start as root 6 over 6, and then root 6 over 3, and then root 6 over 6. So that's 1. And then you will change maybe the x component only. So root 6 over 6 with a negative, and keep the rest. And then you might change the y component. Root 6 over 6, negative root 6 over 3, and then root 6 over 6. And then on the bottom have, again, x change. And then the last one is, not the last one, I mean, they said now we change the root 6. So you have a root 6 over 6, negative root 6 over 3, sorry, positive, and the negative over here, root 6 over 6, and then negative root 6 over 6, root 6 over 3, and negative 6 over 6. There we go. And now to have these guys negative here, so keep root 6 over 6 and then put both of these negative. And the one that will also change the x. So this is the one where it's all negatives. Whatever pattern you come up with. Yay, there they are. Again, plug each in the... I'm not wasting another 30 minutes. Plug each in f of x, y, z. And I'll put here. I'm done. It could be a good exercise if you are tutoring anyone 6th grade. Right? Let's find another example because we can. Oh, by the way, I didn't mention this before. How many constraints can you have? Is it just one? Or you can have as many as you want? Yeah, exactly. As many as you want. So this is cool. So now let's go application. And the first problem on your project is going to be something of this stuff. So it's not a temperature, but so problem 56 from the book. By the way, this problem 95 was from review, not from the section. So chapter review 95. The problem that I'm doing now is from 12.9 section homework. So this is a 56 temperature on the elliptical plate. So the points on an elliptical plate that it's given as x squared plus y squared plus xy less equal than 1. Its temperature is given as temperature xy is 25 x squared plus y squared. So find the min and the max temperatures. So you have a temperature equation. Now see, the temperature equation is not given as, right, your objective equation is not given as f of xy. It's t of xy because it stands for temperature. It's just del t instead of del f. The rest is the same. You can call your constraint equation g still. It's okay. All right, see you then. You all have the same? Was not able to detect any minimum values. All 4 points which I found were a max. Now solving the system, so this means that the Lagrange multiplier doesn't detect max on the minimum value on this disk. Have to find some other way. But let's briefly talk about the way I solve the equations. Do you see that the equations are exactly the same with x and y swapped? So when two equations do that, that immediately means that x is equal to y, because it's the same equation. So symmetry helps solving these problems quickly. And then you just replace each y with x, and you have 3x squared equals 1. So that was the very fast way to solve this. Okay, so now we know we used Lagrange multipliers, and we found that with the constraint of x squared plus y squared, right, this is the ellipse, right, creates a disk. Now we only found the maximum. It is okay to crank 12.8. Maybe that will also give us some ideas of the minimum. But again, to find the minimum temperature of this, right, with the constraint of that, all we got is the 4 points for the max, because they're all the same value, 50/3. And obviously contributing to that are these squares. So whether you have positive or negative, it doesn't matter in terms of coordinates. When you square it, it all becomes positive. Which is interesting. But that's what the calculation gave us. Let's see if we can find other. They don't have. So they have these distance problems. Minimum distance to a plane, minimum distance to a surface, minimum distance to a cone, extreme distances to a sphere, maximum volume of the cylinder in a sphere. So those would be some applied. I wish there was more business application. Again, hopefully the new edition of the book will bring more of the relevant stuff rather than just X and a Y. They have about 80 questions here, maybe 5 of them are useful and the rest is just nonsense. So minimum distance to a plane. Minimum distance to a surface, minimum distance to a cone. Yeah, let's take a look at a cone, whatever. So you have a cone, z squared is equal to x squared plus y squared, right? And that immediately gives you the constraint, right? Because you have some shape in the world. And then you want a minimum distance to a cone closest to the point 1, 2, 0. So you have a cone and you have a point and you want the minimum distance d. This point here is the unknown point x, y, z, which lives on the cone. This point over here is 1, 2, 0, known point. And we have obviously the equation for the cone. Does anyone know the distance formula? Because clearly if you want the closest point, that's going to be the distance formula between 2 points. Does anyone know? Yeah, it was in chapter 11, I know, 7 years ago.
D equals the square root of 1.
Thank you. D equals the square root of x minus 1 squared plus y minus 2 squared plus z squared, because it is just z minus 0 there. So it's 1 point minus the other point, each coordinate squared, add them all up. This is called the Euclidean distance. And the distance is, now you want to minimize this, which creates equation D to be your objective function. So that's your f, and you have your g with the cone. So if I want to translate this now into the language we are used to, we're going to have this as f of x, y, z, and then you have your g of x, y, z equal to x squared plus y squared minus z squared, everything equal to 0. That's your constraint. Now, you can use the original constraint when you start solving equations. You don't have to use the new one down there. But this is your set of 2 equations, and now you go and do your del f, del g, and all of the good stuff. So, like, clearly we are looking for the shortest distance between a point and an object. The object becomes the constraint, and the distance is objective function because that's the one that you are minimizing. So how your partial derivative now? So tricky, is it? Did I mention you should turn your notebook sideways, no? So when I take this derivative, you notice that I put just the square root, which is the square root of everything. Please remember that the derivative of square root of x was simply 1 over 2 root x, right? It's the same. And then if you have the derivative of square root of a function, it would be the derivative of that function divided by 2 times square root of the function, right? So that's what I used. I know that whatever is under the square root will stay unchanged, go into the denominator as 2 times the square root unchanged. It's only the numerator that takes the derivative of what's under the square root. Now, since you have partial derivatives and x is separate from y, separate from z in different terms, only the x survives for the x one as a derivative. So the power drops down, and then the derivative of the inside, which is x minus 1, is just 1. So the chain rule does not change anything. And then the 2 from the square root formula and the 2 from the derivative of the top when the square drops down, they cancel for each one of these. So each one of these square roots that I did not write out are the original square root from the problem. And the reason why I'm not bothering with it is because now I need to solve this system. And as you can see, this system is not simple at all, because we have 3 out of 4 equations to have this really annoying square root right in it. Now, in many cases, I did tell you, kill a lambda, we don't need lambda for anything. But I have to focus my first step differently now, because these are complicated nonlinear equations. What I'm going to do now is I'm going to solve each one of these for square root. And I'm going to equal the first 2, the second 2, first and the third. Right? I just have to equal 2 pairs of these. Right? And that will create new equations for me without these square roots. And then I'll go from there, hoping to be able to solve things. So that's one of the ways. You see that in equation 3, you can eliminate a z by dividing both sides by z. And that's not good. Because in this here, right, z could be 0. And you are not allowed to divide by 0. It would be a different thing if this z represented the length of the side of the box that you are looking for maximum volume or something, right? In which case you know that the volume of the printer, which is a box, cannot have one of the sides to be 0. So that would eliminate, right, the height of the printer to be 0, and then you know that z can't be 0, and you are allowed to cancel z's in a third equation. But now z could be 0, because z equals 0 just meaning, well, I'm walking on this floor. That's the elevation for us, right? Z equals 0 is the floor. It's okay to have the shortest distance between me and the door to go on the floor, where z is 0 everywhere, right? So you have to be careful with application. If you're talking about distances, right? The distance cannot be 0, well, unless it's the same point, obviously. But the location, right, could be 1, 1, 0, right? X is 1, y is 1, and z is 0. That's okay. So you can have a point that has a 0 coordinate. Now, in the context of a different problem, right, where I said that z could represent the height of the printer or whatever, well, in that case, z cannot be 0, and then you can divide by things. So what I'm going to do, I'm going to try to simplify these equations by at least eliminating these square roots by, now, if that doesn't work, well, we'll try something else. So from the first equation, square root is equal to x minus 1 over 2 lambda x. Square root is equal to y minus 2, right? Second equation, 2 lambda y. And the third equation, square root is equal to. And now we have z over negative 2 lambda z. All right, so now that you have this on the same side, this is where you can cancel z's, and when you cancel z's, that feeds into the both equations. So, I mean, right, we have that the square root, these arrows are bad, because now I have the square root is equal to negative 1 over 2 lambda, and now that gets equal to these equations because square root is equal to square root. So I have x minus 1 over 2 lambda x is equal to negative 1 over 2 lambda. And I also have y minus 2 over 2 lambda y is equal to negative 1 over 2 lambda. This equation on top, multiply both sides by 2 over lambda, I'm getting x minus 1 over x is equal to negative 1. The bottom equation, again, times 2 lambda on each side, y minus 2 over y equals to negative 1. The top equation over here becomes x minus 1 equals to negative x, from where 2x becomes 1 and x becomes a half. On the bottom equation, y minus 2 becomes negative y, and 2y becomes 2, and y becomes 2. And now I have that the z squared is equal to x squared plus y squared, x squared, so that's going to be a quarter, plus y squared is 4, and
That's y equal 1.
that's what I said. Please pay attention. No one is paying attention over here in this classroom anymore. I was about to say 5 quarters because I computed it all the way here, but I wrote the wrong thing there. Because I'm going through my head, why is this not 5 quarters? Because I was getting 17 quarters, and I said it's supposed to be 5 quarters. So 5 quarters, and we have that the z is equal to plus minus root 5 over 2. So we actually have 2 points that are equally distant, right, as a minimum distance from the our point, and that's going to be 1/2, 1, and then plus minus root 5 over 2. So that's those are the 2 points that we have that have max. Now you might be thinking, wait, how do we have 2 points, right? Do you remember what the cone equations actually look like? I drew only half of the picture up there. That's not a good representation. If you go back and look in your textbook, the cone looks like this, right? So if you have a point right here, then, right, you have the 2 of these distances that are the minimum distance. Bueno? Yeah, all right, good. So this and this, as you can see, they share the same x component, the same y component, and clearly different z component, where this z over here is at the 0 level. Wasn't that at the 0 level? Yeah, it was, right, in our original point, because it was 1, 2, 1, 2, 0, right? That's 1, 2, 0. That gives you that this quantity over here is 0, and that makes sense, because that's the origin, 0, 0, 0. For our cone over here, 0 squared is equal to 0 squared plus 0 squared, right? So that works. I mean, it's mathematics, obviously. Everything has to work together. So, so there you have it, right? Those are the minimum. Those are the points, and then you actually have to go and compute the minimum distance. If the question is asking you what is the minimum distance, well, you just found the point at which you found the point that connects to the point that you want. So now to find the minimum distance, you have 2 points. Pick either plus or minus; it doesn't matter. So you have 1, 2, 0, and you have 1/2 1 and root 5 over 2, and now you crank the d to get the distance, which you have, right? You have the equation for d right here. You just need to plug those values in, x, y, and z, so 1/2 and then 1, and then 5/4 to compute. I can compute. We're done with this section anyway. So what is the minimum distance? It's going to be 1 minus 1/2 squared plus 2 minus 1 squared plus root 5 over 2 squared, and then this is a half squared, which gives us a quarter, plus 1 squared is 1, plus 5/4, right? All of that actually is square root. So this is 6/4. 6/4, that's 3/2, plus 1 is 5/2. So it's a square root of 5/2. Right? Multiply top and bottom by 2 to get a value that you can work with. It's root 10 over 4. So that will be the minimum distance. But you have to find the location in which that minimum distance go, so that you can use that point and the point where you started when you're measuring from to get these kind of things. And then you can build bridge, right? What's the minimum distance from one shore to another, right? That's that. Good. So your next exam, which we are going to discuss right now, since my left, good. We can. You are definitely going to have Lagrange, and then maybe even the next exam, chapter 13. It's only like 6 sections in chapter 13. It's short. Final exam, the project, labs, they're all going to have, because this is actually what you do eventually. Obviously, you don't do calculations, computer does calculations, but you have to set these things up for the computer. All right, well, that's it. Let's talk about the exam, and then you see when the quizzes pop up.